Let's look at the dispersion relation for the longitudinal vertical equatorial Rossby wave problem we are looking at. Looks complicated, but it's still pretty much the same thing. So here is the equivalent depth, which is the separation constant in this case of vertical longitudinal problem that we have set up. We are going to look at it as a function of the longitudinal wave number as before. And we are also obviously going to look at the vertical wave number, which is clearly related to the equivalent depth as before. As equivalent depth decreases, waves get shorter scale, which means wave number goes up, which means wave length scale also is smaller. So as waves become low wave number or longer scale, the wavelength also increases, the vertical scale also increases, and the equivalent depth increases. So you have to just get used to these multiple dimensions. Okay. As before, we have low wave numbers, low frequency waves with westward group velocity in meter per second for the longitudinal group velocity CGX. This is for meridional mode 1, and there is the wave number at which the switch from westward to eastward happens. So obviously that changes as the equivalent depth decreases, and along with that obviously the wave number increases as well. Okay, so you can see the parallel between the vertical and the horizontal here and the coupling, right? So intuitively it should make sense to you that as for, let's say, for the same wave number of 10 for equivalent depth of 1000 meters, you have eastward group velocity of here 2 meter per second. Let's say this is 6 meter per second. As the equivalent depth decreases for the same wave number, you're going to become slower and slower in terms of group velocity, and eventually you're going to switch, but here the equivalent depth is really small. And you can also do the same thing by going in this direction, fixing the equivalent depth or fixing the vertical wave number. The point is the strong coupling is very clear. This is the relation we are looking at. If you look at the vertical group velocity that goes with it, looks very different. You can see we are only looking at positive wave numbers, which means they are propagating upward, and the group velocity is downward, so it is negative. And you can see that for longer wave lengths, lower longitudinal wave numbers, so low m and low ka is going to put you here in terms of slower vertical group velocities, and then it increases as you increase the wave number, and then it begins to decrease again for the same equivalent depth. But if you increase the equivalent depth or decrease the equivalent depth for the same wave number, you're going to decrease the vertical group velocity as well. But you can see there are large flat regions over large wave numbers for the same equivalent depth. You're going to have wave number, group velocity being the same. What else can I say about this? Yeah, let's leave it there. We'll come back to this later on. Vertical propagation is a little bit more complicated. In the longitudinal propagation, we had a circular pathway you can go around. In the meridional direction, we had to worry about the equatorial trapping and the exponential decay of the solution. You cannot have a growing solution. In the vertical, you can go out of the atmosphere and not grow exponentially, but when you come down, and you hit the surface, you have to be sure that the bottom solid boundary or ocean boundary conditions are satisfied. So there are differences in the way we think about it. Thinking about the mixed Rossby gravity wave now for the longitudinal vertical waves, we again take the equation that I'm not going to go back to. You remember mixed Rossby gravity wave is basically n equals 0 meridional mode 0 in our general dispersion relation. So in that case, we have the dispersion relation looking this way. Again, depending on Doppler shifted frequency, gravity wave speed, longitudinal wave number, and the basic state, which omega in this case can be written this way, right? I'm not going to go into the details because these are long equations. You just have to look them up each time. There is no way you are going to remember them. So in this case 2n plus 1, so n is 0 for mixed Rossby gravity wave. So you're going to get this relation, which you can solve for omega by remembering omega is omega d minus ku bar. We can then just go to looking at the dispersion diagram for the vertical and horizontal as before, as we did for the equatorial Rossby waves. So again, looking at just the positive wave numbers, the inverse relation with the vertical scale and the equivalent depth, they are not the same thing. I hope that much is clear. Okay, so the n equal to 0, another thing I wanted to point out here, I remember now, you have to be careful because these are longitudinal group velocities which are in meter per second, whereas the vertical group velocities are in centimeter per second. This is very important to remember. You have the global circumference of thousands of kilometers being covered by longitudinal group velocities, but in the vertical you have just kilometers to cover, so you have this in centimeter per second. So that's what I was trying to remember. Okay, good that I remembered it. Now, looking at the dispersion relation again, you can see now we are plotting the longitudinal and vertical group velocity vectors. So you can see the change. So mixed Rossby gravity waves have a group velocity that's always positive, and for positive m, the vertical group velocity is always downward, but obviously changes in magnitude greatly based on the wave number or the equivalent depth. So longitudinal wave number or the equivalent depth, which is the same as saying with vertical wave number as well. So that's a slightly different way of looking at it. Okay. We are not plotting m negative here, the downward propagating waves. You can imagine how those curves will look for those. So looking at longitudinal and vertical group velocities separately, again meter per second, centimeter per second, same axis, equivalent depth, longitudinal wave numbers, vertical wave number, and again long waves and low wave number waves in m or in k. You have large group velocities. As waves get shorter, the group velocity decreases, and as equivalent depth gets shallower, wave group velocities decrease, and the same with m. And CG has similar behavior, as you can see, but obviously it's downward propagating group velocity because we have vertically upward propagating waves. So upward propagating waves, energy going downward, downward propagating waves, energy going upward. Somehow you have to get used to it and think intuitively about it. This matters a lot when we begin to look at the real physics of these things. Okay, those are the expressions for the longitudinal and vertical group velocities for the mixed Rossby gravity wave that is plotted here. and this is the same as 7.2, except this is now for Kelvin waves. So looks very similar, except you have you will see that the Kelvin wave is non-dispersive. So in the horizontal, in the longitudinal direction, a given equivalent depth and or a vertical wave number, the group velocity remains the same. So dramatically different from mixed Rossby gravity waves and the equatorial Rossby waves. But the dispersion diagram looks similar. You have eastward group velocity and the vertical group velocity is downward because we have vertically upward propagating waves. So this is the main difference, and you can see the group velocities are much larger here for the same equivalent depth and the same zonal wave number. In fact, we don't go to very high wave numbers here to stay to realistic solutions in the real system. So you can see the group velocities quickly drop off from about 60 here to 10 here, whereas for Kelvin waves you are going from 95 down to 15. And this is what you have to remember, the non-dispersive Kelvin waves. Whereas in the vertical, you still have this relation that is not flat like this. So you have the relation between short Kelvin waves and long Kelvin waves, and dependence on the equivalent depth for the vertical group velocity that is much stronger and non-linear. Okay, so that's just the Kelvin wave relation that I already plotted. I'm just I guess I have misplaced the order of the figures. Nonetheless, this is how the frequency wave number relation looks related to the gravity wave speed of the meridional mode, and frequency here is a function of the vertical wave number. The vertical propagation here is seen as work done by the pressure work done. So it's like P prime, perturbation pressure, times W prime, the vertical velocity perturbation. So that can be derived in terms of variations of CPZ, so the phase velocity in height coordinate, or group velocity in height coordinate as functions of m. Okay. For m greater than 0, positive phase speed, vertical group speed is negative. We can differentiate 710 with respect to m to get vertical group velocities, and that's what we end up with. This is something we have already seen, writing the the gravity wave speed in the vertical, so the Kelvin wave. That's what it looks like, dependence on vertical wave speed and the vertical scale height and ideal gas constants. Okay, so that's the complicated looking group velocity, which states that for positive vertical wave numbers or down upward propagating waves, vertical group speed will be negative, opposite sign of the phase speed, and when m is less than 0, you will get group speed going upwards. So you also have to consider the case of what happens if the waves are forced somehow at the surface. So we'll see that later on. Okay, very good.